Hello, everyone. Thank you for attending Snowflake Build 2025, and thank you for attending my session. My name is Amber Converse. I am a data scientist at HOPPR. We are a startup accelerating the training of medical imaging AI, including foundational models, curated fine-tuning data sets, and much more. I previously worked as a researcher at the University of Arizona, working on the development of LLMs for political science tasks. But today I will be talking about structured label extraction using Snowflake and LLMs. The problem that I'm talking about is just basically this, is we have a large, often dense, free text string. And we want to get out of it some form of structured information. So in this case, we have a chest X-ray report made by the attending radiologist that basically summarizes what was in a series of chest X-rays. And we don't have, say, we want to train a vision model for the detection of lung nodules or for the detection of atelectasis. We don't have the label for whether there was a lung nodule or not. All we have is the report. So in this case, what we want to extract is whether a certain finding is present. So we might extract whether there's a pneumothorax, and in this case there is, or cardiomegaly. And so the approach to this problem could be to use regex, which is very explainable. This is like keyword based. It's easily changed, but it requires some iteration. You have to look at a lot of reports. You have to really understand what's in them in order to know what keywords to use. And you have to be very careful to avoid false positives if something's negated or if there's hedging in the report. So it's very rigid and it's very prone to overfitting. There may be a certain way of wording something that you've never seen before, and so your regex doesn't account for that. So this approach just isn't robust enough for very complex label sets. Another option is to use the fine-tuned BERT model. This is easily replicable. It's deterministic. A lot of these models are very small. You could run them even on your computer, possibly. However, this requires training data. For most other approaches, you might only need validation data. So you just need a test set to know how well your model does. But in this case, in order to fine-tune a BERT model for this to perform well on this task, you will need possibly thousands of reports that were annotated by a human in order to do this. And that means that it's not very easily adjusted based on changing definitions. So if you decide that you want a different label set or you have a different definition for a certain label, you have to make a whole new validation set and train a new model. And it may also have unexpected results on edge cases. So the approach that we went with was using LLMs for structured extraction. So this is using something like Gemini or OpenAI GPT with structured response format. So in this case, we're instructing the LLM to respond with a structured response in like JSON or in YAML. And this approach only requires a validation set. So you need a validation set of labels made by a human to know how well you're doing at this task. But it's easily adjustable based on changing definitions for your labels. Because in this case, the definition for the label isn't encoded in the weights via pre-training or fine-tuning. It's encoded in the prompting. So you can actually change your prompts very easily across runs. So if you need to change what labels you want, that's as simple as just changing your prompt. There's also a wide variety of options and new models coming out all the time, so you can take advantage of that. And you can also take advantage of reasoning and larger model size for very complex tasks. Some of the cons are that it can be more expensive. This can be offset by using smaller models, so like GPT-5 Mini instead of GPT-5, or you could self-host an open source model, something like Llama or Qwen. Both of these are more economical options. Another problem is that it's non-deterministic if temperature isn't 0. So if your temperature isn't 0, you might get different responses for the same report across different runs. And so our solution to building a specific way of using an LLM for structured extraction is to build an experimental harness for structured label extraction using LLMs. So when you're doing this, you need to experiment. And you need to see what works. This is very much an experimental process. And so you need to experiment with different hyperparameters, with different prompts, different models. And you need to be able to evaluate how well each of these do so you get the best settings for your task. And so this harness makes it very, very simple to set up experiments and find the best version. And all of this is hosted on Snowflake. And all of the states are handled via the database tables, including the text that we want to extract text from, the labels that we have that were generated by a human, and all of the schemas. So all of the schemas for the findings that we want to extract are standardized, so you don't have to worry about defining the JSON themselves. So I will give you a quick demo to show you what I'm talking about. This is the text label extraction program. This is hosted on Snowflake. It's got a Streamlit front end. And you can use this in either two ways. Either you can just set up an extraction, say you already know the good settings for your specific task. Then you can just set this up, set your settings, and then do the extraction. But there's also an experimental configuration where you can actually change all of these to be experimental variables. So you can select multiple miles to try and multiple prompts to try. And it will automatically generate all of the experimental groups and run all of them. But in this case, we'll just start with one run. So you can give it a name, call it Snowflake demo, and I can supply a ground truth file. In this case, I'm not actually supplying ground truth labels. I'm just supplying a list of which study IDs I want to generate labels for. So I just define 5, and then I can define parallelism. So in this case, because we're doing API calls, parallelism gives us a pretty huge speed up. So I'll just set that to 5. So we'll do 5 API calls at once. And then I can set the model. I'll stick with GPT-5, but we can choose quite a few different ones. You can adjust the temperature, the tokens, you can add a system prompt. And then here you can select the schemas that you'd like to use. So these are the schemas that the LLM will adhere to, and it'll adhere to all of the ones that you select. So in this case, all of these schemas are just related to the presence of a medical condition in a. So I select atelectasis, cardiomegaly, and lung lesion. So in this case, I'm saying that I want to extract whether there's atelectasis, whether there's cardiomegaly, and whether there's lung lesions in these reports. And then I'll define my prompt. I'll define a very simple one. I'll just say, classify this report according to the JSON schema provided. And then I'll say the report is, and then I will define text. So text within curly brackets for this program just means where the actual report text will appear. And it doesn't have to be the end, it could be anywhere. In a lot of cases, for the best performance on this type of task, you'd like to define what atelectasis means, what cardiomegaly means. But in this case, we're just seeing how well it does with no guidance. All it knows is what we want, and it's going to try to figure it out for itself. And then here we could use some thinking and reasoning, which for GPT-5 specifically gives us a pretty big boost. So I'll just set thinking effort to low. And then I will generate a configuration. And then I can go to run, and I will run this configuration. So for each of those 5 reports that I gave the study ID for, it will make a call to the OpenAI API, and it will call GPT-5 and use it to generate a structured response for each of these reports. And we can monitor the output here. And it's almost done. It just has to do 5. But in this case, the API calls are actually being handled via Snowflake. So these API calls are very sandboxed, and the user doesn't have to care about how it works or about the API keys themselves. All of those are stored on Snowflake. The API keys are secrets, and the call to the API is handled by a user-defined tabular function. But here, Once this is completed, all of these had ground truth labels that a human had made already available. So we can use those ground truth labels to evaluate how well the LLM did when compared to a human. And in this case, it did very well. It got 0.964 weighted F1 overall across all of the categories. But we can see it broken down by finding. So how well did it classify cardiomegaly versus lung lesions? And we can also see it down to the specific label. So in this case, how well did it do at labeling things as present versus absent? And so we can see very specifically where the LLM suffers and where it does very well. But the more interesting way of using this is to actually compare. And here we can actually import the previous configuration that we downloaded and start with here. So we did that run. We saw GPT-5 did really well. So maybe we want to see how well other models did. So let's see how well Gemini 2.5 Pro does. And let's turn on thinking for GPT-5 in 2.5 Pro. In this case, we use a thinking budget instead of effort parameter. This is just the difference between the models. So we use Gemini 2.5 Pro. And then we can also see how well a smaller model does. So how well does 2.5 Flash with no thinking do as well? So we can experiment with a bunch of different models. And then we could also try a different prompt. And so all of these with plus signs, you can define different values for them. And it will automatically experiment with all of these possible values to see what the best setting is. So each time you press the plus sign, you're just defining an experimental variable. And so here, what if we didn't give it any prompting and we just said text? We just gave it the text. So we're not telling it what to do. We just give it a JSON schema and the text. And we'll see how well it does with that. So we generate an experimental configuration. We run it. In this case, we click on the Run Experiment option. And then we get here all of the different combinations of models and prompts. So we defined 3 different models and 2 different prompts. So there's 6 experimental groups. And this can actually get quite large. Like if we wanted to try a couple of different temperatures, maybe higher maximum tokens, we could generate an experimental configuration and it'll generate all of those. So in this case, this can get quite large. There can be quite a few experimental groups. But in this case, we just want the 3 different models with the 2 different prompts. And so we'll test each model against each prompt. And we can give them each a name. So we could say this is GPT-5 prompt 1, and so on. In this case, I'll just leave them at the default because we can see here which ones are the best. Go ahead and run it. And it'll run each one individually and then get the results. So once all of them have ran, we'll get the results. So we'll come back to that in a second because we'll just let that run. But the program is structured basically like this, where we have a Streamlit front end, which is hosted on Snowflake. And the Streamlit front end takes input from the user. So which studies do we want to extract for? What are our configurations? And then it will talk to Snowflake and it will make queries to request the reports for the studies that the user wants to extract from. It'll find all of the schemas and tell the users which schemas are available currently on Snowflake, and also all of the gold labels that are currently available on Snowflake. And then Snowflake will return the most up-to-date information. And then the Streamlit front end will decide which configurations need to be called, and then it'll call the label extraction program. So this is kind of a wrapper around a command line interface that we had before. It'll call that. And then the label extraction program will call Snowflake because it's running on Snowflake in order to make the LLM API call. And then once that's done running, it will return the results to the front end and display them to the user. So for this to work, we need a couple tables. We need the report table, which has a study ID as the primary key, and then the actual report text in the text column. So this just defines all of the reports that we have available. And then we have the schemas table, which contains a few different schemas, and then their definitions in JSON. And then whether they're active or not, in case you want to make them inactive, maybe one is out of date, we don't use it anymore, you can set it to inactive and it won't be shown to the user. And then we have the entries table, which is, I think, the coolest one. In this case, we have a foreign key, a study ID that references which report it's for. And then we have the schema, which references the name of the schema that is being annotated. And so each row in this table is an annotation entry. This is a entry by either a human or an LLM that is attempting to label this study with this schema. And so we have a timestamp, so we can tell what the most recent one was. We have an ID that uniquely identifies each annotation entry. We can tell who made it, what type of person made it. So was it a human or was it an LLM? Was it a regex? And then we have the entry itself, which gives us the gold label. So in this case, that defines that study 0 has a lung nodule present and John Doe said so. So we can use this to decide what the most up-to-date gold label is. And so to use these tables within the code, we query the reports with a pretty simple Snowflake query, where we just go to the reports table, we pull all of the ones that have the study IDs that the user supplied. And then for the ground truth, we create a window that is grouped by the study ID and the schema in the entries table. And then we order them by when they were created. So in our main query, when we filter for only the ones with the study IDs related to the one that we have, filter only for ones that are on schemas that the user has defined, and then we filter only for ones that were done by humans. We then use that window to define the one with the latest date. So we just do a quick row number definition. And so then because we ordered it descending, the first row in each group in the window function is the most up-to-date annotation entry. And then we can select those. And so this relies on your entries table's definition being that you will only add an entry to the table if it supersedes the previous one. If the definition is different, then this query wouldn't work. But in this case, we assume that the most recent annotation for a given schema and a given study is the most up-to-date one. And then the next part is that because this is hosted on Snowflake, it's very sandbox. So we need to define where it's allowed to access the internet and how it's allowed to do so. So in order to do that on Snowflake, we need to define a network role. So this basically just defines a host URL that could be accessed on Snowflake. And then we need to define the API key as a secret. And this means that users can see whether a secret exists, but they can't see what it is. So there's no way to find out the API key from within the database. You can only use it within this user-defined tabular function that I'll talk about. So this makes it so the user doesn't have to worry about the API keys at all. And then we define an external access integration, which uses this API role and the API key in order to define like a whole access to the internet. So we're basically defining the security for how this program can access the internet to make sure that there's no other usage of this program. And then we define a tabular function, which uses this integration to actually do the API call. So in this case, we only use the OpenAI SDK to make the API call, but we define this function which takes the parameters that the user defined. So like the prompt, the system prompt, the model, whether there's thinking or not. It makes the API call, and then it returns a table, which includes the response from the LLM, which would be the JSON string, and some usage information. So we can actually use this user-defined tabular function to track usage and cost. So we can tell how many input tokens were used, how many completion tokens were used, and use that to make sure that costs are within line. And I'll go more into detail on this a bit. And then in order to use the UDTF from within the program, it's pretty simple. You can actually just define your session, put all of the parameters into the query, and then you just do it like any other query. And that will get us back the resulting tabular return value. And we can use that to then parse the JSON and evaluate it against the gold labels. And so the key features of this integration are that it's hosted on Snowflake. So authentication is already handled. That's part of the nice thing about this is we don't have to worry about the Snowflake username or the host. This is already hosted on Snowflake, so the user has already logged in. So we use their current credentials in order to handle any access to tables or anything like that. And data storage and updates are handled on Snowflake as the single source of truth. So the big thing for this means that if you make updates to what the gold label is for a certain study or for a certain label, it's automatically updated, and users who are using the program automatically get updated with the most recent label. So there's no more passing around CSVs with the most up-to-date labels. This makes it so that it's all hosted on Snowflake and it's all up to date. And I think that the sandboxed API access is very user-friendly because the user does not have to worry about how to make the API call or anything to do with API keys. And there's no way for them to access the internet from the program in any way other than you've defined in your external access integration. So now that we've gone over the program a little bit, I'll go a little bit more into some of the code. I don't have time to do a deep dive into all of it, but I'll talk a bit about the tabular function. So this is the full declaration for the tabular function. So these are all of the parameters. So we have all of the parameters basically that the user could define for the LLM call. So we have the system prompt, the model name, the temperature, maximum tokens. So it takes all of these as input plus the base URL. And so the base URL is defining what the URL is that will make the API call to. And what's nice is that OpenAI, of course, has an OpenAI SDK compatible endpoint to make an API call, but so do Google with Gemini models and Anthropic with Claude. So we actually only define one way of making an API call using only the OpenAI SDK. So we don't actually have to import the generative AI package from Google or any Claude package. We only use the OpenAI SDK, and we are able to make API calls in the exact same way for Gemini, OpenAI, and Claude models using this tabular function. So besides that, this is some pretty standard validation. We make sure that there's a prompt. We make sure that the thinking levels are valid. We do some conversion, maybe some wrapping, depending on the type of model that we're calling. And then here we can use the underscore Snowflake library from within Snowflake to get the generic secret string. So this is how we're able to get the actual API key. And this is only visible from within this function. So only the person who defined this function can define how the secrets are even used, which means that your API keys are very safe. And you can use your company AI key and not worry about security. And then we use that to create a client with OpenAI, and we define base URL. And so this is how you're able to call Gemini models from within the OpenAI SDK. And then we make the call itself. And then we record the prompt tokens, the completion tokens, and the thinking tokens, and why it finished. And we return all of that to the user's program. And so that all happens on Snowflake in a very structured sandbox way. And there's no way for the user to maliciously use that. The other thing is that in order to host on Snowflake, you will have to define a few YAML files. And these basically just define your environment for this program. So for this program specifically, uh, we define this YAML file, which defines which external access integrations we'll use and kind of all of the files that are related to the program. And so when you call Snow CLI, which I go into more detail in the README on the repo, when you call that, it will upload all of the files that match these file types. And then we also define the environment. So these are all the libraries that are used on Snowflake. We just define when the user uses this program, what libraries are necessary. Thank you. If you would like to take a look at the full code and go in a deep dive into the whole thing, it will be hosted on a GitHub repo. And if you have any questions, email them to me at amber.converse@hoppr.ai. I like to thank everybody for attending this talk. And I hope that it was very informative. And I also think that while this is very tailored to medical reports, this same strategy of using LLMs for structured extraction can be applied to a variety of domains. This doesn't have to be medical reports. This could be the classic example of extracting movie review sentiment. It could be quite a few things. So if you need any help adapting a similar approach to another domain, I would be happy to help. And thank you.